Awesome. Okay, so for now, for today's session, we'll have some reminders and then we'll dive straight into the first session for today, which is a continuation actually of the fundamental math in quantum computing and a short break and then Python fundamentals for session 2. Now for the reminders, next slide please. Okay, so for BulSU participants, we're done with the registration and the first day attendance. So for today, you will be needing to fill up two forms, the day two attendance and then the homework and feedback form. And then, yeah, we'll continue the session for next year. So the homework will be due on 48 hours, and we suggest that you accomplish this before the holidays, just so that you won't be needing to think about anything after that. Okay? And then, next slide, please. For non-BOSU participants, likewise, we're done with the registration form and the day one attendance form. So this time, you will also need to fill up the two forms, the attendance and then the homework and feedback form. The homework is also due in 48 hours after the session, and of course, we encourage you to finish it before the holidays. And then, if you've accomplished everything, all of the four forms listed here, you'd be able to get your certificate of participation. Although we can't offer the remaining of the BulSU series for you because this is under a particular program in the OST, but we still have some more events here in Quantum Philippines, and we also have a lot more planned out already for the next year. So watch out for future events, not just introductory ones, but even uh, deeper and more in-depth and hands-on ones. Okay, next slide. All right. For the materials, all the materials and recording links will be sent after this session via email. So it might take some time, 1 or 2 hours to process everything. But yeah, so all of these are for personal use only. Reproduction and distribution without permission from us is not allowed. So yeah, you can use all of these materials for to answer all of the homeworks that we'll send later, and for your personal review as well. But of course, we ask that for you to not reproduce or distribute it without permission from us. All right, that's it for the reminders. Again, good afternoon, and we ask for everyone to be go in a place that's comfortable, and yeah, let's listen with an open mind and a logical mind, I should say. And yeah, I would like to welcome Sir Elmer Peramo for our first session for today, the continuation of mathematics fundamentals in quantum computing. Hello po, good afternoon.
Good afternoon, Jabez. Good afternoon, everyone. Am I being heard clearly?
Yes po, loud and
Thank
clear.
you. So, okay, let me just share my screen. Okay, I'm trying to share my screen. Host is disabled.
Hi
I'll
po,
try
Sir
again.
Bob.
Okay, great. Okay. Sharing my screen right now. So, yeah, good afternoon again to all the participants of this lecture series, Quantum Computing Lecture Series. And I hope with our lectures yesterday, we were able to whet your appetite to actually want more. I guess you're not yet tired of all the equations because, like what I promised yesterday, today I'll be talking about complex numbers. I'll continue what I discussed yesterday, since and then whatever I'm going to finish, whatever things that I will not be able to discuss for today, I will continue the discussion
Recording in
next
progress.
year, since we still have another session later tonight about Python programming. So that's going to be a more practical uh, exercise for learning quantum computing. But before that, let me just introduce you to the realm of complex numbers. So yesterday, when I introduced quantum computing or the mathematics behind quantum computing, I didn't include complex numbers. So because I really want you first to get the idea of how quantum computing works and the fundamental concepts with the help of the introduction of the quantum computing concepts from quantum mechanics as introduced by Sir Dylan. Today, we're going to delve with the mathematical rigor of complex numbers. So basically, I'm sure all of you already has a background in algebra. No? In algebra, if we want to solve, for example, a quadratic equation like this x squared is equals to 4, we will just have to take the square root, and the answer is positive negative 2. So there are two real number answer. But what if we are posed with this kind of equation, x squared is equals to negative 4? As you can see, x squared in the real world, in the realm of real numbers, there's no such thing as there's no value of x or real value of x that's really satisfy that equation, because when you see it's already squared, you always think that the right hand side should be positive, but in this case it's negative. So but this kind of equation really crop up with from time to time. So that's why mathematicians from before, they invented the concept of I, or the imaginary number, and I stands for the square root of negative 1. So if I've already invented this tool, I, this contraption I equals the square root of negative 1, we can now solve this equation to be uh, positive negative 2 I. So with that, as you can see, as we understand the real world, I mean, as we navigate our the mathematical world, we were first uh, introduce the natural numbers 0, 1, 2, 3 when we're starting to count, and then later on when for example in grade 6 perhaps we were taught the integers, the realm of integers. So it includes now the negative numbers aside from the counting numbers or the natural numbers. And also we were taught to do the division operation. So that's why if you're going to involve all the integers and the division operators, you will come up with a number that is not really an integer, but it's called a rational number. But the thing is, the denominator or the divisor should not be 0, because that is undefined. So those are the sets of rational numbers. As you can see here, this is a Venn diagram showing you the hierarchy of the different types of numbers. But the superset of rational number is a real number, because there are some real numbers that are not considered rational numbers. For example, if you have a block of wood with the length of 1 meter, and another block of wood with the length of 1 meter, they are orthogonal to each other. If you measure the hypotenuse of that, it's no longer a rational number. But those and we call them irrational numbers. Examples of those irrational numbers are square root of 2, square root of 3, pi, and e, or anything that you cannot express as a quotient or as a ratio of p over q, or where p and q are integers, are called irrational numbers. So, but that doesn't stop there. As you saw before, there are some numbers that we would need to invent to actually solve some tasks or some problems, and that's why they invented imaginary number. And imaginary numbers and plus the real numbers, they comprise the complex numbers. So as you can see here, the hierarchy using this Venn diagram. By the way, this is not accurate. This circle, irrational numbers are actually the complement of rational numbers under R, and imaginary numbers are the complement of real numbers under C, or under the complex number. Okay, so complex numbers are real numbers plus imaginary numbers. The standard form is A plus IB, or A plus BI, where A and B is an element of a real number. Examples of complex numbers, so you usually see this kind of this form. So this is one form. I'm going to show you two other forms of complex numbers later, but this is the most common form. This is of representing a complex number. you have here 2 plus 3i, negative 1 minus I, and square root of 2 plus I times square root of 3. So you have here three examples of complex number. So you can see from that the form, it's in the form of z is equals to x plus iy, where x is the real part and y is the imaginary part. So you can see that the imaginary part always has that I, or it's multiplied by the imaginary number I, which is equal to the square root of negative 1. And you can come up with a function wherein the the input is a complex number and the output is, for example, a real number. So this is the real component part, and this is the imaginary component part, or the imaginary part of the real number. So that when you are asked, for example, let me just go back to the previous slide. To get the imaginary part of this, don't say I times y, just say I. So that's the imaginary part of the uh, complex number. For example, in this case, the real part is 3, the imaginary part is 2. In this case, the real part is negative 4.3, the imaginary part is negative 2/3. And this one, the real part is 6, the imaginary part is 0. And this one, the real part is 0, and the imaginary part is 4. Okay, this for let's do some arithmetic of complex number. Just like in real number, we can do addition of complex numbers. So if we have complex numbers, let's say z sub 1 equals a sub 1 plus b sub 1 times I, and z sub 2 equals a sub 2 plus b sub 2 times I. So basically, you just correspondingly, you just add the real part and the imaginary part, and then get the sum. And then for the imaginary part, the sum of the imaginary part, you multiply that by I. So it's just that straightforward, even with subtraction. Okay, you just subtract the real part with the imaginary part, and the real part with the real part, and then the imaginary part with the imaginary part, and then multiply the imaginary part by I. So pretty straightforward for addition. So these are example of computation of addition of two complex numbers. This is another one. Negative 6 plus 5 is negative 1. 3 plus 1i. So this is 1i is equals to 4i. So the sum is negative 1 plus 4i. This is another example where you can also do you can apply the associative property of addition, just like what we have in the real numbers. This one, so 6 minus 5i. About this one, 1 plus negative 3 is negative 2, and then 9 plus negative 8 is 1. So negative 2 plus 1i. Next, another important property of complex numbers is the concept of complex conjugate. Every complex number has a complex conjugate, and it's easy to compute. For example, given a complex number here, a plus ib, the complex conjugate denoted by this one, a plus ib star. But in some book, they use bar. They use a bar over the expression. But in this case, we're going to use a star to indicate a complex conjugate. So basically, you just change the sign or of the imaginary part. If it's positive, you make it negative. If it's negative, you change it to positive. So that's the complex conjugate. Example, complex conjugate of negative 2